Okay, as far as I remember, I left over that exercise. I don't remember the number, which was show that if a tree has exactly 2 vertices of degree 1, then it is a path. Has anybody tried? Has anybody tried with this? Understanding whether this has or does not have a 2-factor?
It has 2 factors. Actually, the upper vertices do not have any edges and then with each other, and also the lower vertices do not have any edges with each other, but they have with each other.
Okay, that's a bipartite graph. That's because it's a bipartite graph. Okay, but a 2-factor is a spanning subgraph, meaning a subgraph reaching all vertices, such that each vertex is of degree 2. Meaning it is actually a bunch of cycles covering all the vertices and without intersection. Okay, and what do you think about that? You still think that it has 2 factors? And we had also another problem, which was can you have a Eulerian graph with an odd number of vertices? If yes, show 1. If no, prove that it's not possible.
Eulerian graph?
Yes.
Odd vertices.
With the odd number of vertices, me equals an odd number. Is that possible? If it's possible, you should show 1. If it's not possible, you should explain why it's not possible. So they don't give you the answer. And also here, they don't tell you, well, he again showed, if I remember well, 2 factors here. And then we saw that it's not possible to have 2 factors here. Is it possible to have 2 factors here? And again, this I tell you, if it's possible, show me 1. If it's not possible, prove that it's not possible. But the easiest of the 3, remember, is prove that if a tree has exactly 2 vertices of degree 1, then it is necessarily a path. You should try at least. I've already told you, I don't claim that you solve all of these, but please do try. Next time I'll solve them, and it's not nice. I mean, if you have not tried, if I solve them, it doesn't matter very much. It's not that which will make you pass the exam or not. So knowing the solution of something you have not tried is really of no use. So please do try.
The last problem, I think we can, based on the theory we have mentioned, we can find a path from B to U, and the degree of the V and U is exactly 1, and this is the longest path.
Okay, I imagine that you love longest paths. Okay,
yes.
All right. So
And,
U and V are the ones with degree 1.
yes.
Okay, you start from U.
And end with to V. And
Okay.
this is the longest path.
All right.
And the next step is to prove that why this is the longest path.
Now, you think, well, yes. Why is so? It's the longest path starting from U, you mean?
Yes.
Okay.
And then to V.
Well, going to V.
Yes. and
Oh, well, since it's a tree, you have only one path from U to B.
yes,
Okay, and that's it. All right?
yes,
And
that's the longest path. And if we have any vertex which degree has greater 2, greater 2, greater than 2, then we will have a cycle.
Oh, yes, I see what you mean. I think it's anyway a little bit easier than that. Yes, in the sense. Well, what do you have? What do you know about the sum of all degrees? Since it's a 3, the sum of all degrees, how much is it?
2 multiply the number of vertices minus 1.
Minus 2. Yes, multiply by
Yeah.
me minus 1, so 2me minus
The
2.
number of,
Okay.
yeah, the sum of all ridges, all actually degrees.
Yes. But there is something. If you had one vertex of degree at least 3, then what would happen?
We will have more than 2 vertices which has the greater
1. Exactly. That's it. Yes, but I think, I mean, something of your reasoning is necessary, because after that you should say, well, since then all of them have degree 2 exactly apart from those 2, then it is a path. And why is it a path? Because of the longest path. So
Yes.
your path is necessary. Absolutely. But together with the fact that since only 2 have degree 1, all the others must have degree 2 because of that sign. See, putting together things. Iran plus China. Okay. Come on. And what about this? And also the other one, please. It's not so difficult. Does there exist an Euler graph with an odd number of vertices? If yes, draw one. If not, explain why. Here, does there exist a two-factor? If yes, draw one. If no, explain why. No. She's quiet. She's thinking.
This is a graph with all the vertices, and it is Eulerian because it is connected and each vertex degree is even.
Yeah.
And the number of vertices is 5.
Yeah, sure. Was it so? Let me. I don't remember. Let me see whether it was exactly. If it's what I said, you're right. Your solution is much better than the one I had in mind. Let me just check the original statement. Okay. Anyway, as I've stated it, your solution is perfect. Simply a cycle of 5. Oh, no, sorry. Sorry, it was a bit more complicated than this. With the knee even and the epsilon naught, sorry. So, as I stated it, is absolutely correct. A cycle of 5, but the request is different. And an even number of vertices and an odd number of edges, but Eulerian. Okay?
It is not possible because in Eulerian graph we should have the degree of even for each vertex. Okay, so if we enter an vertex, we should go out.
That's possible.
So the number of edges would be even.
Not necessarily. You're not proving it.
How it could be odd, because if you enter, you should go out.
Okay.
So
Now I can give you the solution, now that you have tried. Okay, now you have tried, you have failed, you have learned something. So I'm very happy with it. Okay, we are left with the one of the bipartite graph and the two factors. Okay, all right, think of it. So let's go to this chapter. No. All right. So, vertex coloring says we have seen I must tell you a little bit. Oh, sorry, I've not started this. Oh yeah. I have to tell you a little bit of the story of this thing of coloring, okay? And it all started again with something not important, not economical, not physical, but a sort of a puzzle among students at the University of London. The fact was that a student had to, he was not a mathematics student, but he has a brother who was a mathematics student. And he had to color a map of the counties of England, okay? And he noticed that it was sufficient to use 4 colors for these counties to be colored in a different color if the 2 counties were adjacent by at least an arc of the boundary. Okay, if you have just a point, it's not enough. Of course, if you have, I think there is in the United States a place where they have 5 countries coming together at 5 states coming together at a certain point, and they love to be in 5 and to take each other's hand and be in 5 different states. And okay, South American things. Okay, and of course here you would need 5 colors. Here you would need 6, 7, 8, 9. And so if your common boundary is just 1 point, you cannot have any bound for the number of colors needed. But if you claim that they have at least one part of one arc of boundary in common, then you see that four are necessary, three are not enough, just by this map, okay? With this map, you color this one, this two, this three, and this must be four. And okay, so three are not enough. And we will see in another chapter, planar graphs, that there is quite a lot of work about these things. But out of this, there was the idea, okay, how can I deal with this problem, which became a big problem, just because nobody knew how to solve it. And so even if it was useless, apart from the curiosity of a student, something you could not solve was terrible for mathematicians. And so they had quite a lot of ideas, and at a certain moment, there was one mathematician in particular who had this idea to take what is called the dual, meaning, let's say, take the capital towns of these countries, okay, and make a vertex out of each capital town, and then connect two capital towns with an edge, if and only if the two corresponding countries are adjacent by at least one arc of boundary. Okay, and so instead of considering the original map, you consider the graph. And so instead of coloring the map, you think of coloring this graph on the vertices. And that's why all the theory of vertex coloring came out of this idea for trying to solve the four-color problem. I can also tell you that the four-color problem, which is very easy to state, as you can see, that's interesting because this book was exactly printed while the four-color problem was solved, and it is now the four-color theorem. And you will see that in chapter planar graphs, because they say this is an unsolved problem, and so and so, and we just know that 5 colors are sufficient, but who knows? And these are, and in a footnote they say, oh, they have just proved it, and so they had to correct while it was going to press, okay. But it was strange because it is a horrible proof, in the sense that it's not a proof which can be checked by a human. It has been done by the help of 1,200 hours of the Cray computer, which was the supercomputer at that time. And still now, it's not something which can be checked by hand by a human, okay? Because it was an enormous check by case enumeration, which is the ugliest way of proving things in mathematics. Saying, okay, these are the 5 cases, and now I check 1, check 2, check 3, I check the 5, and so everything is done. There it was something like 600 cases, and each needed quite a long time of computer computation, okay? And so it's a strange thing, because it is an easy thing to state, and now an impossible thing to prove. We sort of believe it, because what could they do? They produced different algorithms for proving the same thing. And so, again, say another program, another computer independently checked the same thing. Okay, so we are convinced that it's okay, but it's the first proof which is not human in the true sense. There are quite a lot of studies of automatic theorem proving, but generally they are theorems without any interest, okay? Or they are already known theorems which have been proved by normal ways, and which can also be proved by automatic reasoning, okay? But the first one, which is interesting because it was an unsolved problem, and was not proved in a normal way is this one, okay? And it's a strange time because there was more or less at the same time, well, no, some 15 years later, there was Fermat's last theorem. You might have heard of that. There was a theorem. Fermat was actually a judge, and he was an amateur mathematician, but an extremely good one. And he left quite a lot of unsolved and unproved theorems because he had quite a lot of interesting ideas. Some were false. He stated that something was true, and it was proved later that it was not like that. Some others were a challenge for big mathematicians coming after him, okay? And only one was left without a solution, and which is called the Fermat's last theorem, which is extremely easy to state. And it's stated like this: there do not exist non-zero integers x, y, and z, such that for n greater than 2, x to the nth plus y to the nth equals z to the nth, okay? And there were 200 of years of trials by mathematicians of all sorts, and it was a very long path to prove it at the end of last century, okay, by a British mathematician, Andrew Wiles, okay? And it is a human proof, but with the very many steps in different areas of mathematics, while Fermat himself stated, I have a wonderful proof of this statement, which I cannot write because he was reading a book about Greek mathematics, and he was inspired to quite a lot of ideas by that book, and one was this idea, and he said, oh, look, here I have this result, and I have a wonderful proof of it, but the boundary, the margin of this book is too tight for me to write it down. And so he did not write down his short proof. Nobody now believes that he really had a short proof, okay? Maybe he had a proof, but which was false, as some of the others that he was convinced he had, okay? But again, something very easy to state and very difficult to prove in a human way all the same. Another one, which is less easy to state, is Poincaré's conjecture that needed one whole century. I state it in a simple way. If you take what is called a three-dimensional manifold, meaning a space which piece by piece is made like this, say putting together a finite number of rooms like this in different ways, this is a three-dimensional manifold. Take a three-dimensional manifold. If in this manifold you have that every loop shrinks to zero, then it is what is called the three-dimensional sphere, which is not a ball, which is the boundary of a four-dimensional ball, okay? Which is, technically said, every simply connected manifold, a three-dimensional manifold, is homeomorphic to the three-sphere. So something which is very easy to state, but we took, again, a very long way through geometry and topology to be proved by sort of a foolish genius in Russia. Genius who refused the Fields Medal, which is the highest possible acknowledgement in mathematics, and the $1 million prize of the Clay Institute, because it was one of the 7 problems of the millennium for which $1 million are still put by the Clay Institute. He won it, but he refused it. And he's not a rich man, no. He lives with the old mother in deep Russia. Okay. And so you have that problem which gave rise to vertex colorings, which is now a full theory, and out of which also edge colorings came. So a K-vertex coloring of G is an assignment of K colors to the vertices. The coloring is proper if no two distinct adjacent vertices have the same color. Same thing as we saw in terms of edges, but here for vertices. Okay. All right. A proper K-vertex coloring of a loopless graph is a partition of the vertex set into K possibly independent sets. Again, you see a connection with something we just saw in another chapter. We had that if you fix a color in an edge coloring, you get a matching. If you fix a color in a vertex coloring, you get an independent set. Okay, so a coloring is a partition of the vertex set into different and possibly empty independent sets. And G is K-vertex colorable if G is a proper K-vertex coloring, and it will be convenient to say, to refer to a proper vertex coloring as simply a coloring. So all vertex coloring will be proper from now on. Okay? And abbreviate. Oh, sorry. K-vertex colorable in K colorable. A graph is K colorable if and only if its underlying simple graph is K colorable. Okay, you have to start by a loopless graph again. Why? Because if you had a loop, then a vertex would be adjacent to itself, and so you could not have a proper coloring in the sense that that vertex would be colored in the same way as an adjacent vertex itself. So again, loops are not allowed. Okay. Or if you prefer, and that will be important in a computation we'll do, if you get a loop, then immediately you have no colorings. Okay? All right, and what happens is that if you have multiple edges, it does not matter. If you have 3, 4 edges, it does not matter. It's the same thing as having one edge between those two vertices, okay? So the problem of vertex coloring a graph and its underlying simple graph is the same. What is the underlying simple graph? The one which keeps just one out of multiple edges between two given vertices. So we just work on simple graphs. It's not completely true, you see, because in a computation which we will do, we'll have loops and multiple edges. But we'll keep that in mind, and so when we'll meet multiple edges, we'll reduce to the underlying simple graph. And if we will meet loops, then we'll say no coloring for that graph. A simple graph is one colorable if and only if it is empty. What's an empty graph? It's not one without anything. It is one which has vertices but no edges. Then only if you have that there are no edges, it can be colored with just one color. Okay? That's understandable. A little less intuitive is that it is two colorable if and only if it is bipartite. But actually it is that in a bipartite graph, I'm sorry that the Pakistani lady is not there. She loves and hates bipartite graphs. But bipartition is exactly the fact that in the graph you have two very well distinguished independent sets, one which is the complement of the other. The bipartition in X and Y is exactly that. X is independent and its complement Y is independent. Okay, and then actually, if you can, but it's exactly what we did at the blackboard when I tried to show that something of the gentleman here tried to show that something was bipartite. It was just a matter of coloring the vertices with two colors. It's exactly the same thing. The chromatic number key, and here you see he instead of he prime, he of G is the minimum K for which G is K colorable. If he of G equals K, G is said to be K chromatic. A 3-chromatic graph is shown in figure 8.1, which is this, okay, in which you have color 1, color 2, color 1, color 2, color 1, color 2 and color 3 necessarily, okay? But you also have the simpler version I have given there. Yeah, I have the time for this part. Okay. Critical graphs are very interesting and we should think about them a bit. I'll give you also this small proof, but first of all we have to understand very well what K-critical means. This Dirac is not the physicist, it's not Paul Dirac, it's his, how to say, adoptive son, Gabriel Dirac. Okay. What is a K-critical graph? Is one that is K-chromatic and a graph G is critical if for every proper subgraph H of G you have that he of H is strictly less than he of G. And what does it mean? Again, think in an intuitive way. Do you have that you have a fixed number of vertices? Do you think that you will have a bigger key, so the need of more vertices, of more colors, if you add edges and vertices, or if you take away edges and vertices?
If you take away, you will need less colors.
Exactly. Okay. So you can understand that if you start with a certain graph, if you start taking away, then eventually your minimum number will actually decrease. Okay. But CDN, you take away all the edges, you are left with the empty graph, and so the chromatic number will be 1. So in between, you surely are bound to diminish your chromatic number, okay? And so you might have graphs like that, such that if you dare taking away a vertex, then what is left has a smaller chromatic number. This is called a K-critical graph. Okay, and every K-chromatic graph has a K-critical subgraph, and a 4-critical graph is shown in figure 8.2. Which is this. Okay, this is a 4-critical graph, meaning a 4-chromatic graph. Here, of course, you can use 5 or 6, but 4 colors are necessary, 3 are not sufficient. And whenever you take away one vertex, what you're left with can be colored with 3. Okay? Now, theorem. If G is K critical, then small delta is greater than or equal to K minus 1. And this proof is nice, even if it's not so elegant because it's by contradiction. Assume that G is a K critical graph with small delta less than K minus 1, okay? Now take a vertex V with that particular degree delta, okay? Small delta is the smallest degree, so there is at least one vertex with that degree, which is less than K minus 1. We are assuming that for proving that something goes wrong. It's a proof by contradiction, ad absurdum, okay? So let's take such a vertex V. But if you take away V, you are left with a subgraph which is K minus 1 colorable. Why? Because G is not a subgraph in any K colorable graph, but a K critical subgraph, okay? So, okay, color G minus V with the K minus 1 colors. So you have the set of colors of vertices colored by 1, the one colored by 2, the one colored by K minus 1, okay? But what happens is that we are assuming that V is adjacent to less than K minus vertices. We are assuming that small delta is less than K minus 1 and that we have taken a vertex with that degree small delta. So V is adjacent not to vertices of all these classes of vertices. One at least is missing, okay? It must be non-adjacent to every vertex of some particular V sub j. But then, what can we do? We can color V exactly with that color J of vertices which are not connected to V itself. But then, what would we get? We would get that there exists a K minus 1 coloring of G, which is a contradiction because G is assumed to be K critical, which, by the way, means K chromatic. Okay? So necessarily, small delta must be less than or equal to K minus 1. Okay? If it is K critical. What can we deduce out of this in terms of a general graph and not a critical one? Every K chromatic graph has at least K vertices of degree at least K minus 1. Why? Let G be a K chromatic graph. Okay, I take this away. Oh. All right, I'll leave it there. Okay. Why? Let's take G a K chromatic graph. So G can be colored with K colors, but not less. And then it contains a K critical subgraph, okay? But each vertex of H has degree at least K minus 1 for what we have just seen. Since it has degree, each vertex of H has degree at least K minus 1, it means that in H there are K minus 1 other vertices, itself and K minus 1 others. So these are K vertices in H which have degree at least K minus 1. Okay? So H has at least K vertices, otherwise it would not be a K chromatic, it would not need K colors. If it has less than K vertices, of course it does not need K colors, and so it has at least K vertices of degree at least K minus 1. And this then, what does it prove? It proves this, that for any graph, He is less than or equal to capital delta plus 1. Why is it an immediate consequence of the corollary? Why? Because the biggest degree is greater than He minus 1. So every K chromatic graph has at least k vertices of degree at least k minus 1, and so the biggest degree is greater than k minus 1. If k is the least possible such k, then capital delta is greater than or equal to k minus 1. Otherwise said, k is less than or equal to capital delta plus 1, which gives us again an upper bound for this number. But this did not help at all for the big initial problem, as we will see a bit next time and a bit later when we talk about planar graphs. So I finish here, but if you have questions, I'll be happy to answer. I think you don't suffer too much if I finish 8 minutes before time. Okay, see you.